Hi, this is the second part of 6.1. The first part of 6.1, we were just verifying identities. This one's got a couple of things going on in this next piece. One is we're going to show that an equation is not an identity. Okay, and that's a little tougher because you actually have to find a counterexample to show that something is not an identity. So if you remember what an identity is, what an identity is basically saying is the left side equals the right side of the equation no matter what, as long as it's defined. Well, to show something is not an identity, you just need a counterexample. And sometimes the counterexample that you try actually works. And if you know it's not an identity, that just means you've got to pick another angle or another number. So this one right here, we're going to take the square root of sine squared plus cosine squared, and that equals the sine of t plus the cosine of t. We're trying to show that is not an identity. So, people who think this is actually true, they're thinking of it maybe algebraically, but it's incorrect algebra because what they're doing is they're taking the square root of sine squared and getting sine, and taking the square root of cosine squared and getting cosine, and then it's putting plus. That rule is not valid in algebra, and it's not valid in trig either, because the square root of a squared plus b squared does not equal a plus b. So that's not even true anyway. But we have to come up with a counterexample. And one thing you can actually do to more convince yourself is do it this way. Sine squared plus cosine squared is 1, because that's one of your Pythagorean identities, and the square root of 1 is 1. Now, the left side is 1, but the right side, sine of t plus the cosine of t, does not always equal 1. And we found many, many examples that if you add the sine of t plus the cosine of t, it does not equal 1. So what I'm going to do, though, is I'm going to pick an angle, and I'm going to know it's not going to work. And the reason the angle I'm going to pick is I am going to pick pi. And you're like, why are you going to pick pi? Well, because I know the sine of pi is 0. Because you remember sine curve, it's 0 right in the middle. And so and the cosine of pi is -1. So sine of pi plus cosine of pi. And if you don't believe me, just look at the graphs at pi. Sine of pi will be 0, and the cosine of pi is -1. And so it's -1. And no matter what, the left side does not equal -1. It's because square root of anything is going to be positive. So, but it doesn't really matter because you know the Pythagorean identity states that inside the radical, the radicand in this case, is 1. Because sine squared plus cosine of squared equals 1. And the square root of 1 is 1, but that does not equal the -1 that you get on the right-hand side. So just that counterexample proves to me that this left side does not equal right side. But this is kind of a no-brainer because the square root of a squared plus b squared does not equal a plus b no matter what anyway. So, but this is a counter proof. This is basically showing something is not. So, but a lot of people when they see this, like I said at the beginning, when a lot of people see that, they automatically think, oh, that's true. So if you missed this in algebra, if you thought the square root of a squared plus b squared equals a plus b, if you think that's true, then you're probably going to think this is true. So, but they're not true actually. So, all right, and this is an angle that shows that they're not equal. So now you'll never make that mistake in just regular algebra either. And what about this one? They're saying that this is not an identity as well. Okay. Now again, what I'm going to do is I'm going to pick an angle. Okay. Now I'm not going to pick pi this time. And you're like, why not? Well, because if I pick pi, because pi plus pi is 2 pi. And sine of 2 pi is 0. Because you remember the sine curve looks like this. Okay, so if I pick pi right here, if I pick pi, pi is right there. And 2 pi is right there. So if you're taking the sine of pi or sine of 2 pi, they're both 0. They're both on the x-axis. So if you put pi in here, pi plus pi is 2 pi. Sine of 2 pi does equal to sine of 1 pi. So you're like, what are you going to do? Well, I'm going to pick another angle because I'm going to pick an angle that's not going to be on the x-axis. Because if I pick pi over 2, And then the sine of pi over 2 plus pi, does that equal the sine of pi over 2? That's the question. So, because this I'm picking t equals pi over 2. You're like, how do you know which angle to pick? That's the challenge. Sometimes you'll pick angles that actually the left side equals the right side. And if they tell you for sure it's not an identity, then you know if they actually do equal, that just tells you you picked the wrong angle. And most likely it's one that's on the x-axis. So this is going to be the sine of 3 pi over 2. Does that equal the sine of 1 pi over 2? Well, obviously not, because the sine of pi over 2 is 1. And the sine of 3 pi over 2, which is right there between pi and 2 pi, is negative 1. And they don't equal. So these problems right here is showing something is not an identity. Now, the one set of problems that I did not put on the board here was to determine if it was an identity or not. That was a little bit more difficult because you don't know if it's an identity or not. And so you have to assume that it is, okay, and try to prove it. And if you can't prove it, chances are it's probably not an identity. And then you go and look and doing the same thing we did over here. So that you assume, because if you try to go the other way around, if you try to say, okay, I'm going to prove this is not an identity. If that actually is an identity, you start trying to pick numbers that don't work, you'll never find one. So what you're going to do is go on the positive assumption that it is an identity, try to prove it, and if you can't do it, then you got one or two things that's happened. You're not proving it correctly, or the thing's not an identity in the first place. And these kind of problems, chances are it's probably is because it's not an identity. It's not a mistake of you that you made. So more likely. So, all right. Now, the next set of problems are what we call trig substitution. These are algebraic expressions, and it has to do with the right triangle. And to be quite honest with you, it's got to do with this triangle right here. Here's theta, and sine of theta is opposite over adjacent. And we know that here because if you look at x equals a times the sine of theta in this particular problem, that means sine of theta is equals to x over a, which means this is x and this is a, because it's the opposite over hypotenuse. Okay? Then this becomes, by the Pythagorean theorem, the square root of a squared minus x squared. So that's what's going on. But the thing is, what we're trying to do with this thing right here is to write this as a trig expression instead of an algebraic expression. Now, I'm going to show you the way the intent of the book is to do it. And then I'm going to show you how to do it by this picture right here. And I think you'll like the picture actually a little better. So, but what you do is this. You take the square root of a squared minus x squared. Well, but what is x? Well, x is by definition how they define it as a times the sine of theta. So if you square the x, it becomes a squared sine squared of theta over x squared, which is a squared sine squared of theta. So what I did was I took the x out and replaced it with a sine of theta. But don't forget, you got to square the a as well. There's a little bit of algebra. Factor the a squared out of this, so it's 1 minus the sine squared of theta, square root of that, over a squared sine squared of theta. Then the square root of a squared is a. And what about negative a? Well, it says a is positive, so we don't have to worry about the absolute value. So it's just a. 1 minus, I'm going to try to do this in one step here. 1 minus sine squared is cosine squared by the Pythagorean identity. And the square root of the cosine squared, so I'm doing 2 steps in one. 1 minus sine squared is cosine squared. And the square root of cosine squared is just simply cosine over a squared sine squared of theta. Now, this can be simplified a little bit more, and it's cosine of theta on top over a times the sine squared on bottom. Now, in my book, it's kind of pretty much done here because you got it in the trig expression, but it can be simplified. The book does go a little further with this, and it's 1 over A times cosine of theta over the sine of theta times 1 over the sine of theta. And that's a little trick because what they're doing is they're trying to peel things apart so that you'll have some of your regular normal identities. And this is actually equal to this because 1 times cosine times 1 is cosine. A times sine is a sine squared. But now you get some typical, that's cotangent of theta, and that is cosecant of theta. So that is now a trig expression. Now, in my book, I think that to me is just fine and dandy. But if you look at this in the back book of Sokowski, they'll probably give it to you this way. So just kind of depends on, you know, how you want to write it. So now, how do you do it by just the picture? Okay, well, if you look at this, a squared, the square root of a squared minus x squared over x squared. Now let's look at that. So if you had this as your original problem, square root of a squared minus x squared over x squared, if you have that, now if you look at this, we have 1 over a times the cotangent of theta times the cosecant of theta. If you try to pull these apart, okay, you can actually get this one by separating this part. Because if you notice, this is one side of the triangle. The x right here is another side of the triangle. So you can actually pull these things apart so that you can actually get the same answer. And right off the top of my head, I don't know, I'm just trying to think of how I could do that. If you do this one up, so this one over this one in relation to this one, that's tangent. So tangent of theta is equals to x over this. So cotangent would be this over this. Okay, so cotangent, there's your cotangent right down there. So cotangent of theta is this over this. You're like, well, this has another x squared on the bottom. I know, because then that 1 over a right there, put together with that x, will get you the other one. It's probably, I don't know, maybe that one is more difficult, but this one is just straight algebra here. So this one actually, I think, it could be done a little easier than some of the problems. I think I picked a harder one in order to do it by the triangle. Sometimes it just kind of falls out by looking at the triangle. So let's stick with this one right here. This one actually works pretty good. So takes a few steps, a little bit of algebra, but if you notice, I took the x squared, made it a squared sine squared because that's what they tell me it is. And then this x squared, same thing. Took the a, I factored the a squared out. And then just a little bit of trig and a little bit of algebra gets me their final answer. Okay, so I have one more problem to do over here. Let me erase this thing right here. I'll move it over just a little bit so you guys can see it. All right. Now, this time x does not equal a sine of theta. It's x equals a secant of theta. Okay, and theta is between 0 and pi. So you kind of do the same thing. So now, let's see here. X squared minus a squared squared. Okay, so we get a squared secant squared of theta, because I squared the x, minus a squared squared, all over a squared secant squared of theta. So all I did here is, whoops, that doesn't look like a theta, does it? There it is. So that looks like a theta now. So now what I'm going to do the same thing I did over here. I took an a squared out of here. I'm going to take an a squared out of those. So if I take an a squared out of that, it's going to be secant squared of theta minus 1 squared. If you notice that outside squared, I'm not touching it. That squared on the outside? Not yet anyway. Now secant squared minus 1, if you notice, that's one of our Pythagorean identities. 1 plus tangent squared equals secant squared. So secant squared minus 1 is tangent squared. So this is going to be a squared tangent squared of theta over a squared secant squared of theta. And on the top, it's not a squared tangent squared. It is a squared tangent squared to the second power. So then now I'm going to pull the squared in. So it's going to be a squared squared, which is a to the fourth. And then that's tangent to the fourth of theta, tangent squared squared. And then this becomes a squared secant squared of theta. Now, tangent to the fourth, I mean, you can simplify it first and say, well, that's a squared tangent to the fourth of theta over secant squared of theta. Now, what you could do, which is what I would probably do to keep from having fractions, secant squared, 1 over secant squared, which is what you have here, you can change that to a squared cosine squared of theta times the tangent to the fourth of theta. Now, I see something that you can actually do with this one. Tangent to the fourth is actually tangent squared times tangent squared. And so what you could do, and it's a little trick, I mean, you might say, can I just leave it like this? Pretty much, because you've got it into a trig expression here. But let me show you a little thing that you might want to notice here. Tangent to the fourth is the same thing as tangent squared times tangent squared. Okay? Now, let me put it back up here so you can see it about right here. So this becomes a squared times cosine squared times tangent squared times tangent squared. Let's write that right there. This is just a matter of just trying to make it look nicer. Then this is a squared times cosine squared. Now tangent squared is the same thing as sine squared over cosine squared. And there's that tangent squared hanging out here. Okay? So the cosine squares cancel. That was the reason I changed the tangent to the fourth as tangent squared times tangent squared, because I knew that tangent squared was sine squared over cosine squared, and that over cosine squared cancels the cosine squared that I already have. So this becomes a squared sine squared of theta times a tangent squared of theta. And this little exercise that I did to try to simplify it, that also shows you that to get good when you get practice that you're verifying identities, it's all about the manipulation. So the reason you try to verify identities is learning to manipulate trig functions from one form to another form. So all I did from this step down here to up here is just getting that a squared sine squared tangent squared is just in a different form. So at some point you have to know when to quit. And so a lot of times I will say, well, just quit when you get it into a trig expression pretty much simplified. And that's kind of leaves a little window of where that's going to be at. So so there's a variety of places that I would have said, that's fine, that's fine, that's fine. So, but it's all about the manipulation. So the only thing is you got to be careful for you guys who love to check your answers in the back of the book. Sometimes when you're checking your answers in the back of the book, even though it might be okay for me, the book may have it in a different format than what I said it's okay to leave it as. So for you guys who are swearing by the answers in the back of the book, it's not going to work out so much for you. So you're going to have to be able to go to that next level anyway. So it's just about how much sure you are of yourself. So, but anyway, this is 6.1, and I want you guys to verify these identities in the first part. I want you to be able to do these, and I will see you Monday. So, and you'll know what I'm talking about in class. So, talk to you later.